Okay, we're going to go ahead and start the next lesson on optimization. Optimization, super important concept in calculus. I think of like all the topics that we look at in calculus as far as having like real world applications. Optimization is probably at the top of the list as far as having like real world applications are concerned. Um, it is like something that we're going to take a look at beyond what we do in class because your second semester memoir project, like the topic is going to be on optimization, and it's useful in a lot of different subject matters. And we'll talk a little bit more about this in class, like later on in the week, and then what your second semester project is going to entail. Okay, so there are two constant themes with optimization problems. The two themes are number one, there will always be an equation that relates your variables. Okay, so you're going to have multiple variables in a problem. You're going to have an equation that relates the two variables. And then the second uh, thing that you're going to have is there will be an equation that we need to maximize or minimize. Okay, and we've talked about like how we find maximums and minimums of functions um, earlier on in chapter 5. Okay, so we're just going to do one example on this video where the directions ask us to find the dimensions of a rectangle with area 1,000 square meters whose perimeter is as small as possible. So when you see the phrase whose perimeter is as small as possible, we're trying to make the perimeter as small as possible. What we are trying to do is find the minimum of perimeter. Okay, so the function that we come up with for perimeter, that's going to be the function that we are in this case trying to minimize. Okay, so just like with related rates problems, I'm going to encourage you guys when you work through these questions here to draw yourself a diagram modeling this. Okay, so we have a rectangle. We don't know the dimensions of the rectangle, so we're going to go ahead and call our base x and our height y. If you want to think of them as length and width, that's fine as well. Okay, what we do know is we know that the area of that rectangle is 1,000 square meters. Okay, and the fact that the area is 1,000 square meters, that tells us the equation that we're going to need to relate the two variables in our problem. We know that area of a rectangle is the base times the height or the length times the width. So with that said, we can set up an equation involving the given information in regards to area. So we know that x times y is equal to 1,000. Okay, so that is your equation that relates the variables. And then we want to come up with the equation that we need to maximize or minimize. Well, if we're trying to find the minimum perimeter, we want to come up with the perimeter function. So if we have a rectangle like this, perimeter is going to be equal to the distance around the rectangle, where there are two side lengths of length x plus two side lengths of length y. Now, the issue that we have here is we have perimeter written in terms of two variables. And if we want to minimize, in this case, perimeter, we want to get perimeter written in terms of a single variable so we can take the derivative of that function and figure out where that derivative changes sign from negative to positive. Well, the way that we're going to be able to get perimeter written in terms of a single variable is we can go to this equation here that I highlighted in yellow, the equation that relates both variables. We can solve that equation for one of the variables. So let's say we solve that equation for y. Oops. So when we solve that equation for y, we get y equal to 1,000 divided by x. And then what I can do next is I can then write perimeter as a function of x by replacing the y in that equation with 1000 divided by x. Okay, so when we do that, we get perimeter as a function of x equal to 2x plus 2 times 1000 divided by x. Okay, which makes perimeter as a function of x equal to 2x plus, I'm going to rewrite the second, like that second product as 2000 x to the negative 1 power, because that's going to make the calculus as easy as possible for myself. Now, we know that for this perimeter function, we know that x cannot be equal to 0. But even more than that, because x represents a side length in this problem, like we can't have negative side lengths for the lengths of our sides in this rectangle. So we're going to instead say that x is strictly greater than 0. Okay, so x has to be some positive quantity here. Now we're going to keep that in mind like as we work our way through this problem. Okay, so if we are trying to minimize perimeter, if I want to find the minimum of a function, we're going to take the derivative and then use that to find the critical points. So the derivative of 2x is 2. The derivative of 2000 x to the negative 1 power is negative 2000 x raised to the negative 2 power. Now I can combine this into a single fraction. So my common denominator is going to be x squared. I can rewrite this as 2x squared minus 2000 all over x squared. And then I can simplify this even further. So I can factor a 2 out of the numerator, which gives me x squared minus 1000 over x squared. And then x squared minus 1000, I can think of that as the difference of two squares. So that's going to be 2 times x plus 10 rad 10 times x minus 10 rad 10 all over x squared. Okay, so once I have that first derivative simplified completely, I can then determine my critical points. So those occur when the derivative is 0. That happens when the numerator is 0. So first critical point is negative 10 rad 10. Second critical point is x is equal to 10 rad 10. And then we also have critical points where the derivative is undefined. And that happens when our denominator is 0, which occurs when x is equal to 0. So when I plot these critical points on my sign chart for P prime, we have negative 10 rad 10, 0, and 10 rad 10. We said earlier in the problem, because x represents a side length in this problem, our side lengths have to be positive. So we're not going to test any values here to the left of 0 because they don't make sense for us in the context of this problem. So if I pick a value between 0 and 10 rad 10, let's say I pick 1, the numerator is going to wind up being negative, denominator is positive, so that resulting quotient is negative. If I pick a value bigger than 10 rad 10 and plug it in, that resulting quotient is going to be positive. So we get exactly what we want here, where the derivative changes sign from negative to positive. Okay, so our minimum perimeter occurs when our side length x is 10 rad 10. And because the side length units, like distance units here in this problem, are meters. And then to figure out what y is, we're just going to plug 10 rad 10 into this equation right here up at the top. We get y equal to 1000 divided by 10 rad 10, which when I rationalize the denominator, we get y equal to 1,000 rad 10, sorry, 1,000 rad 10, divided by 100, and y simplifies to 10 rad 10. Okay, so y is going to be 10 rad 10 as well. So what is the rectangle that minimizes perimeter? The rectangle that minimizes perimeter is actually going to be a square in this particular case. Okay, so that's a bit of an introduction for us into optimization, and then we will work through some more optimization problems as we move through this section. Have a great rest of your day.